Hello viewers. In today's session, we are going to discuss two-way ANOVA. Similarly, like to one-way ANOVA, we will talk about when to use two-way ANOVA, how does this ANOVA test work, what are the assumptions underlying two-way ANOVA. Then with an example, we will be performing a two-way ANOVA. Then we will interpret the results of the two-way ANOVA. And then last but not the least, I will be also discussing few frequently asked questions about the two-way ANOVA. Now, starting with the concept of two-way ANOVA, let's first see what is ANOVA. Although I have already made it clear in my previous session, but still let me tell you that ANOVA, that is the analysis of variance, is a statistical test which is used to analyze the difference between the means of two or more than two groups. A two-way ANOVA is used to estimate how the mean of a quantitative variable changes according to the levels of the two categorical variables which we have taken for the study. So use of two-way ANOVA when we want to know how two independent variables in combination affect a dependent variable. Let's understand this by an example. Suppose we are researching which type of fertilizer and planting density produces the greatest crop yield in a field experiment. So we assign different plots in a field to a combination of fertilizer types. That is one, two, three. That means we have three types of fertilizers. And planting density, that we have two types of planting density. That is one is low density. The second is the high density. And we want to measure the final crop yield in bushels per acre at harvest time. So we can use two-way ANOVA to find out if fertilizer type and planting density have an effect on average crop yield. So when to use a two-way ANOVA is again a question, very important question. Okay. So we can use two-way ANOVA when we have collected data on a quantitative dependent variable at multiple levels of two categorical independent variables. So a quantitative variable represents amount or counts of things. It can be divided to find a group mean. And bushels per acre is a quantitative variable which we have taken. So because it represents the amount of crop produced, it can be divided to find the average bushels per acre. A categorical variable represents types or categories of things. So here we have two categorical. One is fertilizer type and the planting density. In fertilizer type, we have three categories. In planting density, we have two categories, that is density 1 and density 2. And in fertilizer, we have fertilizer type 1, fertilizer type 2, and fertilizer type 3. So now we should have enough observations in our data set so that we are able to find the mean of the quantitative dependent variable at each combination of the levels of the independent variable. So both our independent variables should be categorical. And if one of our independent variable is categorical and one is quantitative, then we can use an ANCOVA instead of two-way ANOVA. So how does the ANOVA test work? Let's discuss. ANOVA test for significance using the F test for statistical significance. So the F test is a group-wise comparison test, which means it compares the variation in each group mean to the overall variance in the dependent variable. So if the variance within the group means is smaller, then the variance between the groups, that is the F test, will find a higher F value, and therefore a higher likelihood that the difference observed is real and not due to chance. So in two-way ANOVA, we can say we can have three null hypotheses at the same time. Okay, like there is no difference in group means at any level of the first independent variable. That can be our first null hypothesis. Second can be there is no difference in group means at any level of the second independent variable. Okay. And the third can be the effect of one independent variable does not depend on the effect of the other independent variable. So we can have three null hypotheses at the same time in two-way. So a two-way ANOVA without interaction, like we can say only tests, and then we can perform these tests to test our hypothesis. So like we will take that example of crop yield experiment and we can test the three hypotheses. So let's see what are the hypotheses which we have framed. Null hypothesis is there is no difference in average yield for any fertilizer type, or we can say there is no difference in average yield at either planting density. And third, we can say the effect of one independent variable on average yield does not depend on the effect of the other independent variable. Okay, so these are the three null hypotheses. Now let's see what can be the alternate hypothesis for these null hypotheses. There is difference in average yield by fertilizer type. So this is against the first one. Then against the second one, we can have there is a difference in average yield by planting density. And against the third null hypothesis, we can have there is an interaction effect between planting density and fertilizer type on average yield. Now, what are the assumptions which are lying when we are taking two-way ANOVA? Again, we have three assumptions: homogeneity of variance, independence of observations, and normally distributed independent variables. So, we all know what is homogeneity or what is homoscedasticity. So, the variation around the mean for each group being compared should be similar among all groups. And if our data don't meet this assumption, we may be able to use a non-parametric alternative like the Kruskal-Wallis test instead of ANOVA. Looking to the independence of observation, our independent variables should not be dependent on one another. That is, one should not cause the other. So this is impossible to test with categorical variable. So it can be ensured by good experimental design. So our independent variables should represent unique observations. That is, our observations should not be grouped within local locations or individuals. So if our data don't meet this assumption, okay, then we can include a blocking variable, or we can use a repeated measures in ANOVA. Normally distributed dependent variable, this is the third assumption. So we take it into account that values of the dependent variable should follow a bell curve shape. That means they should be normally distributed. And if our data doesn't meet this assumption, then we cannot carry out this test. Okay, so we can try a data transformation in that case. Now, taking the example of crop yield, okay, the responses is normally distributed, and we check the homoscedasticity after running the model, and then we come to this thing. So what we will do? Final crop yield we will take in bushels per acre. Type of fertilizers which we have taken is type 1, type 2, type 3 also. And planting density is like density 1 and density 2. And block in the field is 1, 2, 3, 4. So the two-way ANOVA will test whether the independent variables, that is the fertilizer type and the planting density, have an effect on the dependent variable, that is the average crop yield. But there are some other possible sources of variation in the data that we should take into account. So we applied our experimental treatment in blocks. So we want to know if planting block makes a difference to average crop yield. We also want to check if there is an interaction effect between two independent variables. That is it possible that planting density affects the plant's ability to take up fertilizer? So, because we have few different possible relationships between our variables, we will compare the three models. So, a two-way ANOVA without any interaction of blocking variable, two-way ANOVA with interaction but with no blocking variable, and two-way ANOVA with interaction and with the blocking variable. So model 1 assumes there is no interaction between the two independent variables. Model 2 assumes that there is an interaction between the two independent variables. And model 3 assumes that there is an interaction between the variables and the blocking variable is an important source of variation in the data. Now, by running all the three versions of the two-way ANOVA with our data and then comparing the models, we can efficiently test which variables and in which combinations are important for describing the data. And we will see whether the planting blocks matters for average crop yield or not. Now, this is not the only way to do our analysis, but it is a good method for efficiently comparing models based on what we think are reasonable combinations of variables. So now running a two-way ANOVA, as we know that R is an open source, R is easy to run. So I have done my analysis in R, okay, and I have taken a small sample data set for this example. So after loading the data into the R environment, we will create each of the three models using the AOV command and then compare them using the AICT tab command. And for a full walkthrough, we can see to the guide to the ANOVA and R if you want to have more in detail. So the first model does not predict any interaction between the independent variable. So we put them together with a A plus. That means two-way ANOVA. Here is the coding in the R. Okay, so this is how we will write our model. And in the second model, to test whether the interaction of fertilizer type and planting density influences the final yield, we use star to specify that we also want to know the interaction effect. So here you can see the model written in R. Okay. And then we have the third model because our crop treatments were randomized within block. We add this variable as a blocking factor in the third model. So we can then compare our two-way ANOVAs with and without the blocking variable to see whether the planting location matters or not. So now coming to the model comparison, we can find out which model is the best fit for our data using our AIC model selection. AIC calculates the best fit model by finding the model that explains the largest amount of variation in the response variable while using the fewest parameters, and we can perform a model comparison in R using the AIC tab function. So here the codes are given. You can use these codes if you want to do it in the R, and the result output result will look something like this: two-way interaction blocking, K value, AIC value, then delta AIC value, and then we have cumulative weights, and then we have uh, last one is LL. So here you can see AIC model with the best fit will be listed first, with the second best listed, and then on so on. This comparison reveals that the two-way ANOVA without any interaction or blocking effect is the best fit for the data. Now, interpreting the results of two-way ANOVA, we can see the summary of the two-way model and then we can analyze it. Okay. So here we will find some of the most common terms being used in the ANOVA table. First is that although we have done the same thing in the one-way ANOVA also, but I want to repeat it so that it is more deeply rooted in your mind. DF is the degree of freedom. That means for each variable, number of levels in the variable minus 1. Then we have sum squared. It is a sum of the squares between the group means created by the levels of the independent variable and the overall mean. Then we have mean square, which shows the mean sum of the squares. That is the sum of the squares divided by the degrees of the freedom. Then we have F value, that is the test statistic with from the F test, and this is the mean square of the variable divided by the mean square of the each parameter. Then we have P value, which shows likely it is the F value calculated from the F test and would have occurred if the null hypothesis of no difference was true. So from this output, we can see that both fertilizers type and planting density explain a significant amount of variation in average crop yield. That is, p value is less than 0.001. Now doing the post hoc testing, and ANOVA will tell you which parameters are significant, but it will not tell you which levels are actually different from one another. So to test this, we can use a post hoc test, and the most appropriate one is Tokay's HSD test. And this I have done with you in one way ANOVA also, and in two way ANOVA also it is being done. So this output shows the pairwise differences between the three types of the fertilizers and then between the two levels of the planting density, and with the average difference, the lower and the upper bounds of the 95% confidence interval and the p-value of the difference. So from this we can see the values P is less than 0.05 between fertilizer group 3 and 1, fertilizer group 3 and 2, and the two levels of planting density, but no difference between fertilizer group 2 and 1. So as you can see here, the table, this is the output. Okay, so this output will look like this. As you can see, you can also try for yourself. Now, how to present the results of a two-way ANOVA? So now this is very important because results are with you, but how to present it, that is very important. So once we have our model output, we can report the results in the results section. Whether we are writing a research paper, whether it is our thesis, whether it is our dissertation, whatever it is, we can write over there. So this, when reporting it, we should include the F statistic, degrees of freedom, and p-value from our model output. And here we have the model output. Okay, so the increased production under fertilizer mix 3 and at higher planting densities suggests that under field conditions similar to ours, this combination would be most advantageous for crop yield. And the lack of interaction between the fertilizer type and the planting densities suggests that planting density does not affect the ability of the plant to take up the fertilizer. Though at densities higher than uh, this thing which we have taken, this may become the case. So here you can see the post hoc test revealed significant pairwise difference between fertilizer mix 3 and fertilizer mix 1. Okay, so that was 0.59 bushels per acre under mix 3, and similarly between fertilizer mix 3 and fertilizer mix 2, that was 0.42 bushels per acre under mix 2, and between planting density 2 and planting density 1, so which was plus 0.46 bushels per acre under density 2. So now we may also like to make a graph of our results to illustrate our findings. So we can have graph which should include the group-wise comparisons tested in the ANOVA, and with the raw data points, we can summarize the statistics and We can see the letters or significance values above the groups, to which groups are significantly different from others. And we have seen you put values over here like A, B, 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 and C. Okay. So this graph has been done in R. So it might not be possible for you if you are not using R to get such type of graph. Okay. Then comes to frequently asked questions. Mostly people confuse the difference between one-way and two-way ANOVA, which I have already dealt in the previous session. Then how is the statistical significance calculated in ANOVA? And what is factorial ANOVA? And what is the difference between the quantitative and categorical? Although I have answered these questions uh, in the previous session also, again I would like to repeat for you people. Okay. The only difference between one-way ANOVA and two-way ANOVA is the number of independent variables. A one-way ANOVA has an independent variable, while two-way ANOVA has two. And one-way ANOVA tests the relationship between, like, for example, I'm giving shoe brand and race finishing times in marathon. Just like previous examples only, I have taken. Then coming to the factorial ANOVA, okay. So as I have already told you, okay, it uses more than one categorical independent variable, and two-way ANOVA is typical of factorial ANOVA. And some examples, like previous example, we can see the effect of marital status on, let's say, job status and family history. Okay. So likewise, we can reiterate the previous examples. Okay. Similarly, quantitative variables. They are any variables where the data represents amount like height, weight, or age, and categorical variables where the data represents the groups. For example, we can have rankings, binary outcomes, or any classifications we can have. Okay. So we need to know what type of variables we are working with to choose the right statistics, which I have told you uh, in the previous session also. If we don't choose the right variable, all our efforts may go waste, and we may end up with something which was not desired. Okay, so be careful while selecting your test, and before that, you should identify your variables. So, with this, I would like to end up this session of Two-Way ANOVA and wishing you all the best. Good day, and see you again in the next session. Thank you.